Hello, everybody, and you are tuning in for the final AP Physics 2 seminar of the year. This one should be short and sweet. We just got a couple random smatterings of modern physics topics to cover, and then we have done all the material for the course. So last time we were talking about quantum mechanics, and we had this sort of weird idea that matter at its most fundamental level, electrons and protons and such, are not particles in the traditional sense, but they are actually sort of, wave clouds of probability, and sort of the density of this cloud tells you, how likely it is to find the particle at a certain location. So if we're drawing it in this schematic, the electron might be really likely to be in the center here, and less likely to be out toward the edges. And you've probably seen in chemistry, the p and d orbitals that get really weird looking, where you have like a torus with two like lobe-shaped structures here. Like an electron might not be found near the center at all, but might be very likely to be found in this general ring here, or in one of these big, dumbbell shaped things up here. So this would be like this is a d orbital that I just drew. So, different shapes of the electron clouds based off what the electron can interact with and how much energy it has at any given time. So based on interactions and energy, kinetic energy. We were simplifying this to a one-dimensional case where we basically just have an electron in a box, and the wave function, could look like an actual sine function. And so where this function is peaked the most gives us the best chance of finding the particle. Highest amplitude corresponds to the highest probability. And the electron is kind of everywhere and nowhere within these probability peaks until we actually go and measure where it is. And when we do so, we transition to what's called wave function collapse. And the wave function, or the electron, could have been anywhere in this shape here, but when we actually measure it, we find it to peak at a certain location. So measurement sort of calls the electron to be at a specific spot. And we call this wave function collapses. So this is kind of interesting. The fact of measurement itself changes the shape of the wave function and calls the object into being. It kind of gets weirder because even after it collapses, it doesn't stay there. Like we knew where it was at that time, but then, once it collapses, time will pass on and the wave function will sort of revert back to its original state. When you measure something, you sort of specify its position. You can never have a perfectly accurate measurement, but you know that, the uncertainty in measuring x by measuring the position of the particle, its uncertainty goes way down. This is accompanied by an increase in the uncertainty, the momentum of the particle. By figuring out where exactly the particle is, we automatically know less about, how fast it's going. And so by knowing where it is, the uncertainty in momentum decreases. So this is sort of like what a measurement does. This leads us to what is known as Heisenberg's uncertainty principle. which says that the product of your uncertainty in position and your uncertainty in momentum must be less than, or sorry, it must be greater than h bar over 2. H bar over 2. H bar is called Dirac's constant. And it's simply equal to h over 4 pi. That's Planck's constant again. Sorry, not 4 pi, 2 pi. My apologies. 2 pi. This number kept appearing in quantum mechanical equations a whole lot, so people got lazy and they basically just simplified h over 2 pi to h bar, or Dirac's constant. So I guess you could say that this is equal to h over 4 pi. And what this says is that you cannot perfectly know both the position and the momentum of a particle at the same time. Momentum and position are said to be incompatible. Which is weird. This is a uniquely quantum mechanical phenomenon. Like when we did kinematics way back when, we were able to figure out, the position and the displacement of the particle and its velocity at the same time. So we could get the momentum and the position at the same time. Here, Heisenberg says when you are down in the quantum mechanical realm, you cannot measure both of these things at the same time. And there are a number of things in quantum mechanics that can't be measured at the same time. If we go back to our atoms, if you're looking at the angular momentum, L, of those particles, it turns out that the components in the 3 different dimensions are all incompatible with each other. So you cannot measure the x component of the angular momentum at the same time you measure the y component as you measure at the same time as the z component. That is not possible according to quantum mechanics. And there's an uncertainty relationship for these things as well. Delta Lx and delta Ly, actually they have to be greater than h bar times the average value of Lz. So it's weird because the uncertainties in the 2 components actually depend on, the average value that the other component will take. So again, you won't be responsible for this, but it's good to know that, this is how it's usually presented, the uncertainty principle, as a relationship between position and momentum. But in the grand scheme of things, there is an uncertainty principle for any pair of variables that are not measurable at the same time. And in quantum mechanics, there is a lot of them. We can kind of see how this works in terms of, remember we said if we have a slit experiment. So we know that when the particle passes through the slit, it's going through the slit, and therefore the uncertainty in measuring where it is within that slit. We don't know exactly where it is along this boundary, but it's in there somewhere. So its uncertainty in position is essentially the width of the slit. Our diffraction pattern, we said it's spread out the smaller the slit got. So what's happening here? In this direction, this sort of vertical direction as we've drawn it on the paper here, we have an uncertainty in x. As we make that slit smaller, delta x decreases, but that means that our delta in momentum in this vertical direction has to increase as well. So delta p increases, and that allows the diffraction pattern to spread out. So this is true whether we're working with light or whether we're working with actual electrons as a form of the wave function. By putting a particle into the slit we're essentially measuring where it is. We know it has to be within those slits, and so we're putting a small boundary on its position. That means that by specifying its position, the momentum has to increase, and so we don't know how fast it's going up or down here, and it would cause those electrons to spread out, and therefore they all sort of create a pattern as that wave-like nature begins to interfere with itself. So this is sort of our hose analogy again. As we put our finger over the edge of the hose, the water is going to spread out. As we pinpoint where that electron or particle is inside the slit, the pattern is also going to spread out along with that. All right, that's quantum mechanics. In the checkpoint assessment the other day, I threw a curveball at you in the form of this thing called Lepton number. You probably thought to yourself, what the heck is a lepton and why do I care about how many of them there are? I was hoping that the neutron number, the thing that is clearly not conserved in a nuclear decay, remember neutrons can turn into protons and vice versa in beta decay, and so you don't have to have the same number of neutrons you started out with. So that should have been the answer to that one. Lepton numbers, leptons are small particles. Really tiny, tiny things. So this includes things like electrons and those neutrinos. It turns out just like charge and mass and all those other things that must be conserved in anything really, lepton number is a conserved quantity. Meaning the number of leptons I start out with have to equal the number of leptons I end up with. But there's some weirdness to this because remember, when we looked at beta decay, we had positrons, which are the anti-electron, and we had antineutrinos, which are the counterpart of the regular neutrino. Antiparticles have negative lepton number. So if I have a beta decay nucleus, let's say it's carbon 14, and this is going to decay by emitting a positron. And so to conserve charge, I had 6 charges to begin with. I created a positive charge. I need to go down the periodic table to boron to make that happen. So I've converted a proton into a neutron to keep my mass number the same. I produced an antiparticle here. This is a lepton, so this is a -1 lepton number. And so to balance that out, a neutrino has to be created. And this is a regular neutrino, not an antineutrino. And so this is a regular neutrino. So its lepton number is +1. So I have -1 + 1 gives me 0 leptons over here, just like we started with. So if I'm producing an antiparticle, I make a regular neutrino. If I emit an electron, I have to emit the antineutrino to balance out that lepton number. The opposite of a lepton is a small particle. A baryon, from the Greek for heavy, is a large particle. And this includes things like protons and neutrons. While neutrons don't have to be conserved, the total number of baryons does. And so if I have 14 protons and neutrons to start with, I end up with 14 and 0, which gives me 14 to end up with. So lepton number is just it's another thing that you can track in nuclear reactions to make sure things all balance out just right. So that was a little curveball. Maybe it was rude of me to even mention that, but now you know. We can see how conservation laws work out, again, in things like matter, antimatter annihilation. So this happens every once in a while. We have, say, an electron and it meets up with its evil twin, the positron. And remember, these things have the exact same mass. They have the exact, we'll say they have the exact same speed in this case. So they're identical in terms of energy, but they have opposite charges and they have opposite lepton number, I guess. So here's minus or plus 1, and here's -1 for lepton number, which is the opposite of their charges. It's confusing. So when these things crash into each other, they annihilate and they become very high energy photons. These are now gamma rays. So conservation of energy, these things collide, they have kinetic energy, they convert themselves to completely into energy, by the formula E equals mc squared. So all the mass that these things had was converted purely into energy in the form of high energy photons. And now we have no charge. Photons don't have charge, so we have a charge of 0 over here and a charge of 0 over here. And our lepton number, photons are not leptons, 0 and 0, but everything is nice and conserved because this added up to 0, this added up to 0, and we left with 0 in the end. So as long as you are conserving the total amount of charge and lepton number and energy you started out with, these are all legal things that can happen. Two particles can combine with each other to make not particles in the end, photons, light, energy. The reverse can actually happen. We can have energy can form, electron-positron pairs. So the opposite happens. We have, photon that transforms into an electron and a positron going in opposite directions. And again, this had 0 charge to begin with. This had 0 lepton number to begin with. When these things break apart and form the actual particles, plus and minus in both senses cancel out, and this is a perfectly legal thing. This actually is theorized to happen at the edges of black holes in a phenomenon called Hawking radiation, where sort of the energy of that system creates these virtual pairs of particles. And because it's right at the edge of the point of no return of the black hole, maybe the electron gets to escape and the positron gets sucked into the black hole, never to return. And because this particle got to escape, that means eventually, if this keeps happening, the black hole will eventually decay and evaporate. So this is the process by which black holes are thought to evaporate. All right, so the last thing I just want to mention very, very quickly are just to sort of sketch out the 4 fundamental forces. So our 4 fundamental forces are the strong nuclear force. We talked about this one already when we were talking about what goes on the nucleus. It is the force that actually holds the nucleus together despite the positive repulsion there. This is mediated. Each of these 4 fundamental forces, say that 6 times fast, is going to have a particle that sort of carries or mediates this force. The particle for the strong force is the gluon. So this keeps the nucleus together. We also have what's known as the weak nuclear force. It's so weak that it needs 2 particles to mediate it. And these are the W and Z bosons. don't worry too much about what those are. We're not really going to talk about the weak force at all. But the weak force is sort of behind the beta decay processes. So responsible for beta decay. In short, the nucleus decides that it's happy with a certain number of neutrons and a certain number of protons. And if that gets imbalanced, there's a force that has to sort of bring this neutron down to become a proton, or vice versa, to make that happen. So that's a very loose way of explaining what the weak force does in the context of beta decay. We have the electromagnetic force, which we are all very familiar with. It's mediated by the photon. Remember, a photon is essentially a particle that represents an electromagnetic wave. So both the electric and magnetic forces are carried and propagated through space and time by the photon. And lastly, we have gravity. Gravity doesn't really play nice with these other forces. So one of the big problems in physics now is trying to come up with a model that unifies these the two nuclear forces and the electromagnetic force with gravity. Gravity is so far removed from the others that we don't actually we've hypothesized that there's something called a graviton, but we haven't verified that it exists. So that's how out of sync it is with the other ones. We're not even really sure. There's a particle that mediates it. If we're to label these in strength of weak or strong to weak, the strong force is clearly the strongest. The electromagnetic force is the second strongest. The weak force is the third strongest, and gravity is the weakest of all. So not only does it not play nice with the others, but it's also weak. So this sort of outlines the four fundamental forces that govern our universe, their relative strengths with respect to one another, and sort of the particles that are thought to carry them. There was actually recently, earlier this year, an experiment done that might have discovered a fifth fundamental force based off a certain decay process that sort of split a nucleus, or not, wasn't a nucleus. It was as a particle decaying into smaller other particles, and they should have diverged more based off their initial momentum, but there was something else keeping them from doing that. That didn't seem to be electric or another one of the nuclear forces. So I haven't heard much about it since then, so maybe nothing much came of it, but there might be a fifth force that we could start talking about, but mainly it's the big four that we've really understood and studied so far. All right, you've done it. You've completed all of AP Physics 2. From here on out, we are reviewing until the cows come home, and we will all be on the train to Fivesville.